Hi guys, BuildZoid here, and today we're going to be taking a look at the very first X58 motherboard to show up on AHOC. This right here is the EVGA X58 classified, and it should be abundantly obvious why this is getting a PCB breakdown. It's way too damn big, as ATX ends over there. It's got a bunch of overclocking features, and it's got an extremely funky VRM. So yeah, let's get right into it. So starting off with the overclocking features, we've got a clear CMOS button, a power button, a reset button. Well, actually, I'm not sure the power and reset are in that order, but there's a power and a reset button. That's the important part. There's also a speaker that scared the crap out of me when I first turned the board on. I was really not expecting anything to beep, and normally something beeping indicates that there's a problem. So yeah, that was not a pleasant surprise. Though EVGA is one of the few actually I think might be the only manufacturer that consistently puts speakers on their motherboards. Like everybody else just kind of like you might get it as an accessory in the box, but you're definitely not getting it on the board itself. There's also a socketed BIOS chip. There's only one BIOS on this entire board, no dual BIOS on this. Here we have a postcode, very helpful for any kind of troubleshooting when overclocking. Also, because this is a motherboard intended for 4-way SLI, and putting everything down here basically means that if you run 4-way SLI, you're not going to see the postcode, you're not going to be able to reach the buttons. EVGA includes a little OC panel, sort of, well, yeah, a little panel for overclocking that for the overclocking features that plugs in onto this. And that just gives you the postcode, the power button, reset button, some very basic voltage controls, and some PCIe enable disable jumpers, away from the motherboard so that you can use that functionality without, well, having to squeeze your fingers under whatever GPUs you're running. So, and then wonder if you're pressing the right thing or not, because you obviously can't see what you're trying to hit. Um, Anyway, so yeah, that's a nice feature to have. Then up here we've got more PCIe enable disable jumpers. So these are just for troubleshooting any PCIe device, but primarily the idea is if you've got a big multi GPU setup with the GPUs on like water cooling or something, then it's a real pain to remove a GPU that doesn't work. So you can just pull a jumper and test which GPU is causing the post issues or whatever. I also use that on air cooling because I'm just that lazy. Yeah, also up here we've got an X-Cool jumper, which is for extreme cooling, and that, as far as I know, just preloads some LN2 voltages. It doesn't really do anything more than that. And also I've heard that those voltages are not necessarily optimal for all CPUs, but that's, as far as I know, pretty normal, as like every single sort of, LN2 mode jumper out there is just like these settings should work for like 99% of CPUs, and then there's obviously some exceptions. There's also a bunch of colorful LEDs up here. Unfortunately, I have no idea what they do, and I couldn't really manage to find any information in the motherboard manual for what they're for either, which is kind of annoying. Speaking of LEDs, we've also got LEDs by all of the PCIe slots, which are there just to indicate that those PCIe slots are active, because, if you're enabling and disabling them over here, then that's what the LED is for, to tell you if the slot's disabled or not. Though I would like to point out that if you're running 4 GPUs, you're not going to be able to see those LEDs. So they're kind of in the wrong place. In my opinion, they should have been by the jumpers and not by the PCIe slots. We've also got a Molex power connector, which is just for providing extra power to the PCIe slots, because 24 pins are not designed for much more than like 200 watts of power on the plus 12 volts. Well, it depends on which variant of the 24 pin you have, but even with the high current variant, it's just generally better if you're not trying to power 4 GPUs through a single 24 pin. That doesn't tend to go well. So we do have the Molex power connector to provide extra 12-volt power to all of the GPUs that this motherboard can support. Then above the DIMM slots, we've got a bunch of voltage read points hiding up here, and also a I-limit jumper for disabling the overcurrent protection on, I assume, the VCore VRM, because I kind of doubt any of the other voltage regulators have have an overcurrent protection that's low enough to actually cause issues. So yeah, there's an I-limit jumper there. Or it disables overcurrent protection on everything, which, in my opinion, would be the better way to do things. It's just like disable all OCP. Why just disable the safety features of the VCore VRM? Disable all of the safety features. That's always the right way to do things. And I think that covers all of the sort of OC features, right? Postcode, yeah, clear CMOS, socket, yeah, yeah, okay, so with that out of the way, let's talk a little bit about the PCIe slot situation here. So this motherboard's obviously called the the X58 4-way classified because it was designed for running 4-way SLI. And as a requirement for X58 motherboards to support 4-way SLI, you needed these two chips right here. So these are NVIDIA NF200 PCIe switches. Why do you need them? Because NVIDIA needs more money. That's why you need them. So X58 has 36 PCIe lanes coming off of the I/O hub over here. So that would normally that's plenty of PCIe lanes for 4-way Crossfire. That's plenty of PCIe lanes for quad SLI on literally all the later platforms. But back in the day, NVIDIA still made NF200s. So if you wanted a quad SLI license, you needed to pay for a pair of NF200s as well as the quad SLI license. Because, well, actually, like, you need to pay for an SLI license just in general. That's just a thing that NVIDIA sells because they're NVIDIA and they couldn't help themselves if they didn't charge you for things. And then the NF200s is just an extension of that where it's like, technically, quad SLI doesn't need a pair of NF200s, as you would know if you've run a Z77 motherboard with quad SLI support, or I think even Z68 boards with quad SLI don't bother with the NF200s. Like, there is a lot of motherboards out there that support quad SLI and don't have a pair of NF200s, or come anywhere near the number of PCIe lanes that this motherboard has after the switches. But with X58, NVIDIA was like, well, we make NF200s, and they're not like, and outside of dual GPU cards, there's not really much you can sell these with. So just force motherboard vendors to use them for quad SLI support. So, yeah, that's why we have two NF200s here. And that's why it's also converting the 32 PCIe lanes from the I/O hub all the way to 64. Now, obviously, PCIe switches do not increase your bandwidth. They just make the existing bandwidth more, the allocation of the existing bandwidth more flexible. So, this is very much, like the thing is, I bought the motherboard because I think it's cool, not because I think this is actually a good feature. It's just kind of like, well, you're not gonna get, like, there's not really many X58 motherboards that are bigger than this. So, yeah. Other than that, with the what else did I want to talk about? Oh yeah, what the other thing I want to mention about the NF200. So I know nothing about X58 overclocking, but I've heard this from a lot of people who do know something about X58 overclocking. The NF200s are terrible for X58 overclocking because apparently they don't support very high PCIe clocks, and if my understanding is correct, you need high PCIe clocks to be able to run high BCLK. So if you want to do BCLK overclocking and your motherboard's got a pair of NF200, or a single NF200 for that matter, it doesn't matter how many there are, as soon as you have one, and if you can't disable it, it's going to screw you over because it doesn't support high PCIe clocks. So not only does your motherboard cost more because NVIDIA wants to sell you wants to make quad SLI licenses more expensive than they have to be, said quad SLI license also makes the motherboard worse at overclocking because NF200s suck. Yay, NVIDIA. It's a lot like G-Sync, It's like where G-Sync initially needs this really expensive proprietary NVIDIA scaler for the monitor, and then eventually NVIDIA was like, you know what? We'll just support we'll just support G-Sync on FreeSync monitors too. Right? Like similar with the NF200s is just like for years you needed NF200s, and then suddenly with like X79 and later chipsets, NVIDIA was like, you know what, we're bored of selling NF200s. You can just run quad SLI without them. And it's just like, seriously, guys? Like, what? Like, yeah. So NVIDIA really liked selling unnecessary junk for motherboards. But, that's just NVIDIA things right there. That's pretty normal. Anyway, let's talk about the very funky VRM. So this right here is the VCore VRM. And it's a real 10-phase, which is sort of like, which isn't even the funkiest part of it. You might be like, wait, real 10-phase? Isn't this board ancient? How does it have a 10-phase controller? Well, the thing is, Volterra is what happened. So this chip right here, this is a VT, And for that matter, there's actually a 12-phase controller from UPI that I think is even older. There's a 12-phase controller from UPI that I think you find on like 58 HD 5870s. So actually, like, it's kind of funny. Around, like, basically you can there. I'm not sure about the dates for this, but basically you could get up to like a 12-phase controller for a while, and then eventually all of those went away and you couldn't go past 8 phases for a very long time. And then more recently, we're now starting to see again the 10-phase, the 12-phase, and the 16-phase controllers. Though previously there's never been a 16-phase as far as I know. But anyway, this right here is a VT1185MF, and I can't get any documentation on it because it's a freaking Volterra chip. And Volterra likes doing two things: making very funky VRMs and then not having any documentation for them for the public. So yeah, I absolutely love Volterra VRMs, but this is a real 10-phase controller. And the way this VRM works is very unique, and honestly kind of confusing. So let's go over this. So there's a digital interface that goes from the master chip to the smart slaves. So these aren't power stages. Like, power stages are really dumb compared to these things. Even the smart power stages are really dumb compared to a Volterra smart slave. And these are VT1185s SF. The S, and that's a terrible 5. There, that's a much better 5. So the S stands for slave. So we've got, our VT1185 smart slaves. And so the controller connects to the smart slave number 1 through a digital interface, and then that smart slave connects to smart slave 2, which connects to 3, which connects, and so on and so forth until you get to 9. 9 connects to 10, and then 10 connects back to the VT118MF. The point of this interface right here is just to detect how many phases there are, detect any faults. It's not actually used for controlling for controlling the smart slaves basically at all. It's just used for like how many, on startup it's used to check, hey, how many phases there are, and it goes, okay, there's 10. Then it sets the phase spacings, and that's it. And then it's used for just fault detection. So that's already pretty funky, but it gets funkier because on like a regular, like say international rectifier or intersil controllers, you're gonna have like a PWM line per power stage or per phase, right? Well, actually, yeah, you're gonna have a PWM line per phase, and then you're gonna have current sense lines per phase, and essentially you end up with chips that have a bajillion pins, because if you want to hook up 8 phases with a modern controller for 8 phases is gonna have 3 pins per phase. And so you end up with like 24 pins dedicated just to connecting to the actual power stages or the drivers or whatever. To the phases, because if you have power stage, details. Point is, you need a bajillion pins. Volterra, not a fan of having a bajillion pins. So instead what they came up with is they have a clock connection where essentially there's just a signal that goes to every single one of the smart slaves and just tells them what frequency to run at. And that frequency tends to be very high. So this VRM defaults to 804 kilohertz switching frequency, which is way up there considering the year that this motherboard is from. It's not that you couldn't get high frequency power stages, it's just that even now most power stages are optimized to run at 500 kilohertz. That's where they hit peak efficiency. And so you don't really want to build a VRM that runs above that. Volterra, on the other hand, they by design went for 800 kilohertz. That's what we're aiming for. So so you have a clock line that goes to every single one of the smart slaves, and then we get to the actual control. So, and this is the part that absolutely just goes way over my head, and I don't know how it works, but instead of on a regular controller, the controller sets the duty cycle of each phase. Here, the VT11885MF, so this monitors the voltage on the output of the VRM, or at the CPU, not literally on the motherboard. There's a backup circuit for the motherboard, but there's, it's monitoring the voltage at the CPU through the dye sense. Yes, X58 CPUs had dye sense. Unfortunately, there was not really any reliable way of like at the time nobody bothered with like trying to get the data out of the controllers. So X58 motherboards are just kind of awful when it comes to reporting, like monitoring voltages, and that includes the voltage read points. Like those are just connected to the PCB of the motherboard, not the CPU. So yeah. Anyway, so this monitors the voltage going into the CPU, and then somehow it does but like it has to do some kind of fancy math because it doesn't tell the power stages what duty cycle to run at. Or actually, we should need to not call these power stages because they're very not power stages. So instead of telling the smart slaves what duty cycle to run at, which would make them not smart, the controller tells these how much current they're supposed to output over another connection that's literally just an analog voltage level. So essentially, you have another connection that goes to every single smart slave, and you might have like, and that range is like there's a voltage range on it. I can't remember the lower boundary, but the upper limit is like 1.6 volts. So essentially, the controller can be like, hey, 1.2 volts on that analog line, and then there's like through through some resistor set configuration. The smart slaves will translate that voltage level into a current, like how much current is supposed to flow through them. So essentially, like if the CPU needs 200 amps in this scenario, the 1185 MF somehow figures out that it needs 200 amps. I don't know how it does that, but somehow. And then it tells all of the smart slaves to output 20 amps each. And then each smart slave does its thing to get to that 20 amps output, which is just like very weird. Like, it is completely over my head. Like, this is not like every other controller just sends a duty cycle directly to the power stage. This right here doesn't set the duty cycle. So the smart slaves do that themselves. Like they do all of that on their own. And yeah, I am very confused about how this works. I'm also very interested to see, like, I really want to take some scope shots of like this VRM versus some of the other X58 motherboards, because I'm interested in X58 as a platform just in general. So I am picking up some X58 boards for comparison, for doing comparisons. And yeah, this VRM right here is just the most unique control scheme I'm aware of. Because yeah, like I still don't even really get how it's supposed to work, but it gets better because not only do we have this really weird low pin requirement control system, which I think is the main reason why Volterra goes for something like this. And I've just realized that the order in which I drew all of this is not going to work out. Like, I wanted to get rid of that line, but oh well. So that line gets to stay. So not only do we have this very funky control scheme, the actual VT1185 SFs are just bare silicon, which is kind of neat. So normally you have an epoxy package on basically everything that's kind of fragile. These are just kind of bare silicon. The idea being, well, if you just have bare silicon, the thermal transfer from the junction of the power stages to the heatsink is going to be more efficient, and therefore their internal temperature is going to be lower. And I keep calling these power stages, even though they are very, like, these are borderline, like, these have way too much intelligence in them to be considered power stages. Like, they do not work like power stages at all, but I'm just too used to calling, like, they look like freaking 3553s, okay? Like, I can't help myself. Or, well, they're rectangular like 3553s. 3553s have a regular epoxy package. But anyway, so these are bare silicon, which is done for like better thermal performance, which is pretty neat. And then we get to the very funky inductors, because, Volterra just can't be normal. It's like, well, the funny thing is, actually, I think most voltage regulator manufacturers would love to do coupled inductors. They just can't, because Volterra has the patent on that. So yeah, Volterra's the only ones with coupled inductors. Now, what's so cool about coupled inductors? Well, the idea, so in a normal non-coupled VRM, if you turn on the high side MOSFET of phase 1, then the current through phase 1 starts to increase. Meanwhile, the current through literally all the other phases is decreasing. Now, with the coupled inductor, if you turn on phase 1, the current through phase 1 starts to increase because you turned it on, like there's the high side connected. But because the core of all of these inductors is like this is one core with a bunch of inductors in it, essentially what happens is the increasing current flow through phase 1 induces a magnetic field in the core, which is normal. That's what happens with normal inductors too. But because this core also is shared with all the other phases, that magnetic field now induced into that core induces a current in all the other phases that are sharing that inductor. So phase 1 here turns on, and current through phase 1 increases, current through phase 2, 3, 4, 5, and well, all the way down to 5 also increases. And unfortunately, there's, well, I don't know that unfortunately, but because of how this works, there's a limit that you can't actually have. For a given duty cycle range, you can't have more than a certain number of phases in this, which is why this isn't like one giant 10-phase coupled inductor, but 2 5-phase ones. Because if you tried to do like a 10-phase coupled inductor, there'd be some duty cycle problems that you'd run into. That would make it not work very well. But yeah, here, so the idea behind doing this is that essentially instead of having a really what this achieves is that it spreads the current from turning when you're the current ramp when turning on a phase between all of the phases. So it improves efficiency. It allows for a lower effective inductance. So this coupled inductor is rated as being a 50 nanohenry inductor. This is the other part that I can't so the effective inductance is basically, that means you have really low, really good transient response, because you don't have a lot of inductance. That means you don't have a lot of an overshoot. You don't really have the VRM can respond very, very quickly to changes in current demand because the current slew rate is really high. But this is also effective inductance because this is like a design inductance from Volterra rating. If you actually measured each individual sort of inductor in this that shares this core separately, not in an actual voltage regulator application, they measure much, much higher inductances. So this one up here is going to be 365 nanohenries on its own, and the middle ones are 400 nanohenries something, if I remember the data sheet correctly. So yeah, so you can actually get documentation for the inductors. You can't get but unfortunately that documentation isn't very detailed because again, Volterra has patents on it, where the documentation's literally you're not supposed to use these inductors with anything else but Volterra voltage regulators, which is just well, I guess I guess it's probably pretty easy to enforce that, right? Because you can just check, is this a Volterra Smart Slave? No? Well, that's a lawsuit. So yeah, anyway, but the inductance, so that there's an open circuit inductance rating in the data sheet, and that actually is much, much higher than the sort of effective inductance of the whole coupled inductor, which I assume is down to the fact that when you turn on phase 1, it induces a current through phases 2, 3, 4, and 5. And the same goes if you turn on phase 3, it induces a current in 1, 2, 3, 1, 2, 4, and 5. Because 3 obviously is increasing current because it's turned on. So yeah, and because of that, induced current in the other phases, the effective inductance is really, really low, which means great transient response. And also also you get an efficiency improvement relative to how low the inductance is, because if you wanted an actual 50 nanohenry per phase non-coupled inductor, the RMS current, so basically if you reduce the inductance of an inductor, the current ramp through the phase when it turns on gets much, much steeper, which essentially means the peak current flowing through the phase goes way up, and that really harms the efficiency, which is one of the main reasons why you don't see 50 nanohenry, uncoupled inductors in VRMs. It's just not a very efficient way of doing things. And also why a lot of motherboards and stuff hover around sort of the 200 to 400 nanohenry range instead of going really, really low, because really low inductances translate into some pretty awful, potentially quite awful efficiency. But yeah, with coupled inductors, you can effectively have a 50 nanohenry inductor with none of the downsides of a 50 nanohenry inductor. Oh, and it's smaller. That's another benefit, is like if you wanted, you know, an equivalent amount of equivalent individual inductors, they would take up some more space than this does. So yeah, this is like, yeah, like everybody would love to use this, but Volterra has the patent. So unfortunately you don't see Volterra VRMs these days like at all. Which is kind of like, at least not on anything, not on like motherboards or GPUs in the consumer market. There might be some server stuff that still uses this, because Volterra's owned by Maxim Integrated, which is a pretty big like electronics components manufacturer, as far as I know. And yeah, so, but the thing is, I've never seen a Maxim integrated like VRM on a motherboard either. So, well, no, I don't think I have. So, yeah, it's just like, these used to be really popular. Like, there used to be quite, well, not a lot of motherboards with these, but AMD reference GPUs for ages and ages and ages would use Volterra VRMs. Though generally they wouldn't go to 10 phases; they'd be like 4 to 6. But yeah, so this thing is like funky because 10 phase, funky coupled inductors, funky smart slaves, funky control scheme from Volterra. So very interesting VRM. Now let's talk about the actual efficiency, shall we? And that is where this is actually kind of disappointing, because these, and well, again, I can't actually get documentation for the 1185 SFs, but I have seen documentation for some 35 amp smart slaves from Volterra, and the peak efficiency on those is 90%, which is honestly terrible. Like modern, like if you compare it to like modern motherboards, peak efficiencies can, go up to like 95%. So something with like 90% peak efficiency, and that's at relatively high output voltage, is just kind of like, well, that's not great. But yeah, I unfortunately can't get the documentation for these exactly, and these are 40 amp smart slaves, not 35 amp. So to try get, to get a rough idea of how efficient, like how much heat this VRM would put out, I've just used the efficiency curves for the International Rectifier 3553, which is a much more modern part, probably way more efficient than these. It's also a dumb power stage instead of like, well, like it's it's not a dumb power stage. It's a pretty clever power stage, but compared to a smart slave, you ain't got like, power stages are just generally dumb. Because power stages, like the smartest power stages, can do things like, oh, monitor their own temperature or something like that. And the smart slaves can do all of that. But the smart slaves also set their own duty cycles, whereas power stages don't. So anyway, yeah, but these are 40 amp, so I'm just using a 40 amp power stage that also comes in a relatively similarly sized package. So the efficiency shouldn't be that far off, but at the same time, like, Volterra designs for 804 kilohertz switching frequency, whereas the 3553 is designed for 300 kilohertz, and it's just like, and I'm just keeping the efficiency curve from 300 kilohertz, because if I adjusted it down for 800 kilohertz, the efficiency of this VRM would be so low that it doesn't make sense. Like, no, like, considering that other Volterra design, like the Volterra had 35 amp power stages that were also designed for 800 kilohertz and did 90%, it doesn't make sense that they would have a 40 amp that, at 800 kilohertz is absolutely atrocious. So yeah, essentially I'm not very happy with this, but and even then the VRM efficiency is not great, because 10 40 amp power stages, even if I'm using a more modern part with probably a better efficiency curve, like 10 40 amp power stages is not up there in terms of VRMs these days. And I don't know how this actually compares to other X58 motherboards, but I do have other X58 motherboards that I will be doing PCB breakdowns of, so we'll see. Maybe over time we'll come to the conclusion that as weird and interesting this as this VRM is probably not that efficient. Or not that great in terms of actual raw power handling capacity. So anyway, let's go over the, very theoretical efficiency figures. So for 1.4 volts output, 800 kilohertz switching well, it doesn't really matter because I'm actually using the 300 kilohertz curve from the 3553. So anyway, we're gonna assume that it's at 804. So actually, no, we're gonna do this. There. That makes me happier because it's not actually 800. Like I'm just using an efficiency curve that makes sense to me. Might be completely wrong. 3553. There. Anyway, so 100 amps output. This VRM will probably put out about 12 watts of heat. That's assuming it actually hits 92% efficiency, which I kind of doubt, but at the same time, it's like if you shift the efficiency curve down at the low loads, then it would also come down at the high loads most of the time, and then it's like at the high loads, it's just like you couldn't call it a 40 amp part anymore. So, yeah, but anyway, 200 amps, you're going to be looking at about 26 watts of heat, which is not great. 300 amps is going to be producing about 52 watts of heat, which is like, well, that seems very in line with my expectations for a VRM from this time, like for a VRM like this from this time period. Also, it's worth noting that EVGA made a e-power using this style, like actually I think almost like this VRM configuration, and they sort of said that design is capable of outputting 350 amps, which makes sense because apparently, like theoretically, by my estimates, at 400 amps, this will probably produce about 100 watts of heat, which is about 85% efficient. Which is very hot. So 350 amps is somewhere in between those two, and given enough airflow is actually doable. Like that's the thing is like, yeah, 70 watts of heat coming off of a VRM sounds terrible, and it is. Like honestly, you can design VRMs that do a much better job in terms of not producing that much freaking heat for that much current output. Just look at any modern GPU, well, modern high-end GPU or modern high-end motherboard. And this board was high-end at the time. It's just like Volterra literally doesn't support more than 10-phase configurations. So, and I don't think you could do, like, now that I think about it, you probably couldn't do the whole Asus put 2 power stages in 1 phase thing, because these are smart slaves. Like, I don't think they would, like, that would probably cause so many, yeah, that would not work. That would definitely not work. So basically, if you were using a Volterra VRM, this is about as good as it gets, unless Volterra made some better power stages at the time. I mean, better smart slaves at the time, but it's impossible to find out. Like it's Volterra, you can't like. There's no parts catalog. There's nothing, which is really annoying. So yeah, so this VRM's efficiency, like by my estimates, pretty terrible, and realistically, probably pretty terrible, because the e-power, like the e-power board that EVGA sort of said like is 350 amps output using this VRM design is like they also expect you to use like a 5,000 RPM delta fan on it to cool it, at which point it's like, yeah, I mean, if you throw that much air at something, then it's not really like the fact that it's really inefficient is not really that much of a problem anymore, right? Like it's kind of like, well, if your VRM is garbage, then just water cool it and it won't overheat anymore. It's just like not technically a solution, right? It's like if your VRM's not efficient enough, just throw more cooling at it. Yeah, that seems to very much be the approach with this right here. So, not a fan of the efficiency, but a very funky VRM, and a VRM I really want to get some scope shots of because, yeah, it should be really, really interesting to see what this like how this compares to other X58 motherboard designs, because the other ones, the other ones use a lot more conventional voltage controllers with much more conventional control schemes and much higher inductance inductors. But the thing is, also most of the other motherboards use way more output capacitance than this. Like this has a lot of multi-layer ceramics on the output, which, should further help the transient response. We've also got this pro-adlyzer over here. This is from, that's a Nippon Chemicon pro-adlyzer. And actually, that's all of the capacitors on this motherboard are Nippon Chemicons. which is a Japanese capacitor manufacturer. MSI likes using them these days. EVGA has since switched over to Nichicons, which is also who like Gigabyte and Asus use for their high-end boards. And ASRock also uses Nichicons. So anyway, so that's basically a very low ESR, very low ESL polymer capacitor right there. The downside to these, however, is that they come in very low endurances. So this one, for example, is like 1,000 hours at 105 degrees, which makes me wonder, like, depending on what kind of life the board had before it got into my hands, like, there's a good chance, and this also goes for the other X58 boards, like, there's a good chance that most of the capacitors on them are gone in terms of being, like, well, okay, not completely gone, but they could be like, well, the thing is, like, after 1,000 hours at 105 degrees, one of these pro analyzers can be as much as like twice, can have as much as twice the ESR that it's supposed to have, which is quite bad. And then it's like, well, but 1,000 hours isn't very long, so, you know, and the board's ancient. Like, I think it's like 10 years old now, probably, or 9. So that pro analyzer might be very, very not useful at this point. Same goes for all of the other capacitors for that matter, because yeah, the boards are old, and that's another, like, a concern I have for all the other X58 boards I have, is just like, if some of those were just constantly used for like rendering, or, well, actually no, one of them is in really good condition, for that I know is in really good condition. But some of them is just like random X58 boards you find on eBay are like, wonder what condition the caps are in. So when I do like the oscilloscope shot, like oscilloscope measurements, that's one of the things that I'm wondering about, where it's like, you know, the results might be really thrown off by the fact that the boards are so old. So yeah, but anyway, pro analyzers are cool. We don't see them anymore because ultimately you can just get polymers that are much, much better than they used to be. Like the regular through-hole capacitors have just gotten so much better over time, and you can also get SMD aluminum polymers with higher endurance ratings and similar ESRs and ESLs, and you can get more of them for less cost. So yeah, these just don't make sense anymore. But back in the day, this was like the ultimate capacitor for filtering your output power, especially for dealing with like fast transients from something like a CPU or a GPU. So yeah, and then of course on the back of the board we still have the usual multi-layer ceramic capacitor array in the CPU socket. So that's not really any different from what you'd normally expect. Though the funny thing is, the original intention of pro analyzers was not to be well, you can definitely put them on the power plane, just kind of like we see here, but the intention of them was that you could replace all of this with one pro analyzer. And then there are some GPUs that do that, but a lot of motherboards don't. But there's also a lot of GPUs and motherboards that don't do that. And I assume the reasoning for that is like GPU cores potentially get really hot. And similarly, CPU sockets can get really hot. And so the last place you want to put your low endurance capacitor is right behind the hottest part, like potentially one of the hottest parts of the entire motherboard or the entire GPU is like, yeah, that's the last place you want to put the pro analyzer, because that thing is going to be dead much quicker for being that near to a, you know, to a heat source. So yeah, but still, you know, cool little capacitor thing over there. And that pretty much covers everything I want to talk about for the VCore VRM. So let's move on to the other VRMs. And this video is going to be so long. So here we've got the QPI Link VRM, so the QPI VRM, which, as I understand it, most X58 overclockers call the VTT voltage, which I find really confusing because obviously I'm used to VTT referring to memory termination, not like the interface between the CPU and the I/O hub, which a lot of people call this the North Bridge, but at least the official Intel documentation is like, nope, that's an I/O hub, which I guess you would still be able to call a North Bridge, just because the main reason the North Bridge is called the North Bridge, at least as I understand it, is because it's north of the South Bridge, right? Like it's north. So Anyway, so that's the QPI VRM over there. That's a two-phase controlled by this chip over here. And that's a standard good old-fashioned two-phase. None of this fancy coupled inductor, smart slave, Volterra garbage. Actually, it's not garbage. Like, that's a really cool VRM. It's just not particularly efficient. But then, I don't think there was really any X58 motherboards that were that efficient in the VRM department. Anyway, the controller here is an ISL 6... What? No, that's IOH 6312. Yeah, which is a controller you actually see on like that. I think I've seen on other X58 motherboards as well. Also used for just power, like for controlling the QPI link VRM. So yeah, and that's just a two-phase. And there's nothing really special going on with this. We have a low side, a high side, and the MOSFETs are for the low side. We have a, what is that? KO392 from Renesas, and that's a 3.5 milliohm RDS on low side, which is pretty low. Could be lower, but that's pretty low. At the time, that's actually probably very low, because, well, there's been a lot of, like, the thing is just, like, the way very low RDS on MOSFETs are generally made is you just put more MOSFETs in parallel. The problem with that is you end up with very large gate capacitances, and then it's really hard to switch them on and off quickly. So you can get like MOSFETs with like fractions of a milliohm of RDS on, like right now. The problem is you would never put them in a VRM because they take forever to switch on and off. So yeah, anyway, 3.5 milliohm, I'd assume for the time period was actually pretty low. Just because even right now it's not great, but it's better than what you get on some low-end motherboards that come with like 4 milliohms of RDS on. Which are the motherboards that I always say, like, could you please not buy this? It's freaking, like, and the thing is, it's just like, I don't even know why they don't swap them out for slightly lower RDS on low side MOSFETs. It's not like there's a huge cost difference as far as I can tell. At least looking at, like, third-party resellers, though, you know, obviously the manufacturers buy directly from the MOSFET manufacturers, so probably they have some price, like the pricing is going to be different from motherboard makers from like me trying to check component prices. Anyway, for the high side, we're looking at a K03B 2, oh no, B9, which is also a Renesas high side MOSFET. And this VRM should be able to output 20 amps while producing about 2 watts of heat, 35 amps while producing about 5 watts of heat, and 50 amps while producing about 9 watts of heat. And I'm not going to write that out because it doesn't fit on the freaking picture anymore. Next to that, we've got the IOH VRM. So I assume the power from this actually goes both into there and into there. Like, because that, as far as I can tell, just powers the entire QPI link. So yeah, but the I/O hub, that's this one here, that I think only powers the actual I/O hub itself and doesn't power the CPU at all. Might be wrong about that. Again, don't know that much about X58. Hopefully, over time, I hope to get better at it. But anyway, so the I/O hub VRM is a single phase. Did I identify the controller? Oh yeah, the controller is an ISL. Where is it? Where is the controller? Is it on the back? No. Okay. Oh, wait, that's this one, isn't it? Yeah, that's chip. That's this one. So that's an ISL 6545, which is a single phase. Man, my fives are absolutely incredible. And so you might notice there's 3 MOSFETs in this, and the idea behind this is you have a high side and 2 low sides, and by putting 2 low sides in parallel, you cut down your RDS on, and so your conduction losses get significantly reduced because most of the current going through a VRM goes through the low side MOSFETs. So if you have less RDS on, you have less power loss due to current flow. Anyway, so this actually achieves similar efficiencies to the QPI link. So, but it's ever so slightly worse because it does lack the extra high side, and then also, like, in reality, like, I don't account for, like, power losses through the inductors, and having 2 inductors reduces those as well, and so, yeah, this is actually quite a bit less efficient, but it's not, like, a huge amount. For 20 amps output, this will produce around 2 watts of heat. For 35 amps output, it'll produce about 6. Whereas, of course, the QPI link was producing about 5 for 35 amps output. So, I mean, the QPI VRM was producing about 5, not QPI link. The QPI link is what connects the CPU to the IOH. Anyway, so that's the IOH VRM. So let's go over to the memory VRM. That's controlled by this chip over here. I have no idea what that chip is. It has one of those stupid part markings that if you punch it into Google, you're never going to get anything. So yeah, that's great. But it is a 3-phase, but impossible to identify. For the MOSFETs, we're looking at the same kind of situation. Actually, low side, high side, low side, high side, low side, high side. We're looking at the same kind of MOSFETs as we saw in the QPI and the IOH VRM. So again, the K0392 and K03B9 from Renesas, except now in 3 phases. And this can do, oh boy, the orange on the red really doesn't work. But this can output a, what is it, 20 amps while producing about 2 watts of heat, 30 amps while producing about 3 watts of heat, and 40 amps while producing about 5 watts of heat. So plenty of power for, you know, DDR3 overclocking. What I find really interesting about the power delivery for the memory on this board is this inductor right over here. And the reason I find this inductor really interesting is because it is connected to the memory power plane, but there's no active components anywhere near it. And so it can't, like, it's definitely not a phase. And my theory on what this is for is this is supposed to block transients either from the memory controller going towards the DIMMs or from the DIMMs going towards the memory controller. As in, if a memory stick suddenly pulls in, tries to pull, like the memory sticks have a really nasty transient every time they refresh. So when the memory stick refreshes, it just pulls in a bunch of current for that refresh operation. And by putting this inductor here, my theory is it prevents that current spike from going towards the memory control, towards the memory controller on the CPU. So instead, it forces all of that current, like it. Well, it doesn't block it completely, but it suppresses a good chunk of it. So that is one thing I want to check with the oscilloscope as well. Is probably like take a measurement of, probably just like the VDDR pins on one of the DIMM slots, maybe this one over here, and then one of the VDDR capacitors behind the CPU socket, and see what kind of difference there is when in terms of the voltage regulation. Because this is the, well, no, the X58 classified, the regular X58 classified also has this inductor, but this is unique to the classified boards from EVGA having this inductor here. Like, I've not seen any other X58 motherboards with that. So, yeah, and I find it very strange because it's just like, why? Like, you don't normally have inductors on memory power planes. That's just not a thing. So I really wonder what that actually is there to do, because like, that's the only thing I can think of is, like, it's supposed to suppress current spikes from either the memory controller or the memory from reaching one or the other. Because otherwise, it's just like, why don't you just have a regular power plane like everybody else? Why is there an inductor in it? Or I assume the inductor's in the power plane. I don't really, like, desoldering through-hole inductors sucks, especially on, like, high layer count, high power boards like this. So I, like, you know, you could potentially like try to desolder the inductor to figure out why it's there, but I really don't want to do that on a board like this. Way too risky. Also, that's a very big and chunky inductor, so that thing's gonna, like, the inductor itself is just gonna take a ton of heat, and then the fact that you have a board like this is just like, yeah, no, I'm just gonna, you know, try an oscilloscope measurement, but I'm not actually gonna removing that inductor seems like a terrible idea. So, yeah. Oh, I forgot to mention there's a clear CMOS button on the rear IO, in the rear IO as well. So if you have the motherboard in a case like a normie, you can clear the BIOS without having to open up the side panel. And there's also an EVBot header, which that I guess gives you some voltage control functionality at a sort of physical level. So you don't have to go into the BIOS or use like a Windows utility to control voltages. You can just use the EVBot instead. Over that header. So yeah, that is the X58 four-way classified from EVGA. Should be, like at this point, it has to be really obvious why I wanted one of these. This is a very funky board. It's too big. It's got too many PCIe slots. It's got a very interesting VRM, and then this, I will know why this exists. But yeah. So that's the four-way classified. And that's it for the video. So thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon where you can support me. There's a link to that down in the description below. There's also the AHOC Teespring store, which achieves the exact same thing as the Patreon in terms of supporting me, except unlike with the Patreon, you actually get something in return, like shirts, stickers, posters, the usual YouTuber merch. So yeah, that's also an option. There's a link to that down in the description below as well. So that's it for the video. Thanks for watching, and goodbye.